Okay. Hi. So I'm Hiroki from the University of Tokyo and the company Automated Machine. And in this talk, I want to talk about the serial automata and the reaction-diffusion system. And especially, I want to show that the Lenia, actually he developed that, but exists somewhere between serial automata and the reaction-diffusion system. Okay. Let me start with this background, but actually you don't need that, but there are two main approaches for the pattern formation. One is the serial automata, and you know that the famous game of life. And in this case, the update of the each cells should need the state of the cells, surrounding cells. And then it's getting continuous, and it's getting, this continuous serial automata. And one of the very characteristic patterns inside the serial automata is glider like this. And also, on the other hand, there is a reaction-diffusion system. As you know, it is, firstly kind of mathematically formulated by the Turing, and the actual formulation is this one. So this is the differential equation, which just consists of this diffusion term and then local reaction term. And just by this very local reaction, we can get this kind of nice spatial pattern. And also you can implement this one using actual real chemical substances like PV reaction. And here comes our main topic of this talk, Lenia, actually developed by Bert here, and very nice contains serial automata. So it's serial automata, but very smooth. And the very important point is that you can see this kind of glider pattern, but also if you slightly change the parameter, there appears such kind of spot patterns, which resembles more like a reaction-diffusion patterns. So I thought that Lenia is serial automata, but also it should be deeply related to a reaction-diffusion system. That is my intuition. And then I go on to hypothesize this following hypothesis. So actually, Lenia is serial automata, but I think this should be essentially reaction-diffusion system. That is my hypothesis. And then in this talk, I will show slightly different version of this, but actually I will show a variant of Lenia for asymptotic Lenia is actually essentially an RD system. And I will show this by actually implement asymptotic Lenia by an reaction diffusion system. Okay, so how can I implement Lenia by a reaction diffusion system? First, I want to review the algorithm of the Lenia. So this is the algorithm of Lenia. So first, you need some spatial pattern, which is described as Ux. And then first, you need a kernel convolution, which is, here is the kernel. Usually use some kind of donut-like pattern like this, and apply the convolution procedure to this. You get this kind of blurry patterns. And then you plug this into some kind of some function, and then you add this to the original concentration with some coefficient dt. It's like kind of Euler method in the differential equation. And then this one is a bit tricky, but here appears the clipping procedure, which means that the resulting value exceeds, let's say 1, exceeds 1, then the value automatically clips into 1. Or if you get a negative value, it should go back to 0. This is clipping procedure. And then just repeating this procedure, you can get this nice picture in Lenia. Okay. So our task is to, so this whole procedure can be summarized by this single equations like this. And then my task is to convert these equations into this form of reaction diffusion system. Okay, so this is I want to show you in this talk. But there are two main problems which seems impossible to do this. And one is one problem is that the Lenia is actually not temporally continuous. So this is pointed out by in the last ALIFE by Davis and Bongard. They say that Lenia depends on the size of the time step. So if the linear is temporally continuous. Of course, if you have a large time step, it doesn't work like usual method. But if you decrease the time step, it also doesn't work. So it means that the linear is essentially not temporally continuous. And also, we repeated this effect. So if we say the time step dt equals 0.5, it doesn't work, but it's okay. But in the immediate time scale, it works. But if you decrease the time step to 0.002, it doesn't work, which means that linear is not temporally continuous. And this is because of this splitting procedure. So without this one, this whole equation can be directly converted back into differential equations. But with this special procedure, prevent this kind of transformation. So so the conclusion here is linear cannot be translated into reaction-diffusion system because it is not temporally continuous because of this splitting procedure. So what is the solution? The solution is that we decided to use another variant of the linear called async linear. It was also present in the last ALIFE by Takashi and others. And here is the actual equation for the async linear. And you can see that the equation is very much similar, but there is no clipping procedure here, which means that you don't need to care about this temporary continuous thing. And actually, these are actual patterns of async linear. So many patterns exist in the linear can also be replicated in the async linear. So it can be a good, alternative for the linear. So actually, you can convert this one into the differential equation. It's okay. And also we double check that this async linear is not much influenced by the change of the time step. So it seems like, okay. So first problem is solved. But second problem seems much more larger, which is about the non-local kernel convolution. So here is the equation for the async linear, and here is kernel convolution. And in order to calculate kernel convolution for this, for example, for this the center of this part, actually we need the information of the neighbors. Especially, we need the concentration of this wide range of neighbors is necessary to compute this value. So we need a local information for this calculation. But on the other hand, reaction-diffusion system, we don't have that because in this equation, this is just diffusion, and this is just local reaction. So all we have is just this very local information. So what we have to do is just using this local information, but we have to somehow calculate this something which requires non-local information. So it seems impossible, but there is a trick. And this is based on the idea by Lenia and others in 2017. So actually, this is a bit complicated, but what I want is some kind of function which can convert delta function into this non-local kernel. This is the procedure in the kernel convolution. But in order to calculate this by reaction-diffusion system, we added some extra components in the system. Here we call this dj, and j goes from 1 to n. And then here is the equation for each component. And the difference among the different components is this coefficient dj. So this is the kind of diffusion coefficient. So if you set diffusion coefficient very large, then the resulting converged patterns have a wider kind of distribution. And if you set this one very small, it has a very small width in the converged distribution. And actually, these series of functions can serve as a basis for the symmetrical function. So if you nicely choose this alpha 0 and alpha j and superpose each other, then we can emulate the non-local kernel. That is the kind of trick. But of course, there is also another big problem, which is it takes time. I mean, we have to wait this other function converts into this function. But in the original version, this function should be calculated instantaneously. So we cannot wait for long. So here is what is the solution to this? Is just make this reaction much faster compared to the main reactions. So here is we added this 1 over epsilon term. So if you set epsilon very small, then this reaction is going much faster and faster. So it's essentially takes no time to calculate this. And then we can approximate this current composition using the superposition of these extra components. So this is the trick. And then we have all ingredients to implement Lenia using a Reaction-Diffusion system. So I will show you the actual implementation of our system. So here is the original equation in the form of the differential equation of the asymmetric Lenia. And now we can approximate this kernel convolution term by the superposition of extra components, Vj. So we can just substitute this one here. And also we need some more equation for the extra components. So here is the kind of resulting reaction diffusion equation. So you can see that here is the diffusion term. And the other term is just using local information. So this is just a local reaction term. So this whole system is completely reaction diffusion system. Okay. And then we simulate this one with 128 grids. And then we have to set epsilon very, very small. So we set this one 0.005. And also for that, we have to use very small time step. So we set the time step of the Euler method for 0.0001. And then just run this simulation of the differential equation. And here is what we got. So you can see that this glider patterns is keep moving in this simulation world, just using reaction diffusion system. And then it is very short video, but as I said that I use this small dt value. So actually it takes 4 million time steps to get this result. But this is because, this system cannot see very small area around it. So in the original asymmetric Lenia, each cell can look beyond these wide ranges, but in this simulation, it's completely local. So you can only see these surroundings. So it's very incredible that, each cell only see this very small region, but still that whole simulation can sustain these large structures. Okay, then I successfully showed that asymmetric Lenia can be implemented by reaction diffusion system. And then natural question after this that, okay, then whether we can implement this system by real chemical components or not. And I don't have much time to discuss this one, but actually for this RD Lenia, I have to say that this cannot be replicated by our actual chemical system because for that, there is another constraint for this reaction term. Then usually we assume this reaction term should be obey mass action law. And there is a kind of condition whether some function is obeying mass action law or not, based on it is the kind of condition for negative cause effect. And detailed discussion is in our paper, but we can see that this is impossible to resolve this condition in our cases. So this RD Lenia is unfortunately cannot satisfy mass action kinetics, which means that it cannot be implemented by actual chemical reactions. Okay, so here's the conclusion. So we implement the async Lenia, not Lenia, as a reaction diffusion system. So it's kind of real reaction diffusion system. So it just use local information, but unfortunately, this is not a chemical origin system. And actually, in our paper, there are 2 other additional topics, but one is we show that mathematical equivalence of kernel Turing model, which is a kind of phenomenological model of Turing pattern, and asymmetric Lenia. And also we provide a detailed explanation about the chemical probability. So if you're interested, please also check our papers. So thank you for your attention.